topic is 01 knapsack problem. Here some objects are given. For each object there is some profit and some weights are also there, and there is a bag of capacity 15 m. And the objective is, the problem is to fill the bags with those objects such that the total weights of the objects included in the bag should be less than or equal to the capacity, that is 15. And one more important thing is, if you are taking any object, then you must take the complete object or don't take it at all. See here, the weight of this object is 4 kg or 6 kg. So I cannot take 2 kg or 1 kg out of it. I must take the complete object or don't take the object at all. So the problem is, the total profit gain should be maximized. So it's a maximization problem. This problem can be solved using greedy method also, dynamic programming, and even using backtracking. But here in branch and bound, we can solve only those problems which are minimization. Here the answer we want in maximization. So we can convert the signs of these profits. Instead of positive, we will make it as a negative weight, negative profit, and we can solve this one. So maximization problem can be converted into minimization and solve, and then again the result we can convert it back into positive. So let us see how to solve this using branch and bound. So I'll generate a state space tree, and here I'll be using LC branch and bound. LC branch and bound means always I'll be exploring that node whose cost is minimum. Now, for solving it using branch and bound, for each node in the state space tree, we have to find out upper bound and the cost. So we define it as sum of all the profits. Right, I takes values from 1 to n. But the total weight should be less than or equal to capacity of the bag. Same way, cost also will do the same thing. We'll take the sum of all the profits. But the difference in these two is that here we will take it without fraction. Here we will take with fraction. Though the problem doesn't allow us to take fraction, but only for the computation, for solving the problem, we take the fractions. Fraction will not be included in the solution. Now let us generate a state space tree, but I should consider one more thing. What type of solution I want? Do I want the subset of these objects, or I want all those objects and just show included or not included? For example, if the solution, do I want like this, first object included or third object included like this, or do I want the solution like this, that is first object included, second not included, third included, fourth not included? If I represent the solution as a subset of those objects, it will be like this, or else I can show zeros and one for all the objects. So this will be a variable size solution, as the fixed size solution. So I'll go with the fixed size solution, that is zeros and ones I'll be taking, right? So I'll be generating the state space tree for this type of solution. First of all, I'll take something called upper, which is infinity. Now the first node, calculate cost and upper bound for this one. Let me show you how to calculate the cost. For calculating cost, first object's profit and its weight, then the second object's profit and its weight, and next object's profit and its weight. So if I take this weight total, it is coming up to 12. Now can I include the fourth object also? It will exceed the capacity of the bag. So don't include that one. Then how much I can include? 15 minus capacity is 15 minus 12 is 3. So I can include 3 more kgs. So let us say 18 by 9 into 3. So this will be 2 and 6. So how much it is? 10, 20, 32 and 6, 38. So the cost is minus 38. As I said that we have converted this maximization problem to minimization. So we'll take the weights and upper bounds and the cost as negative. Now what is upper bound? So I should take the same way, but don't include fraction. See, the cost was with fraction and the upper bound is without fraction. So if I take this same thing, 10, 20, 32. So this is minus 32. And I got one upper bound that is smaller than infinity. So let us change this to minus 32. This is the first node. Now let us continue with other nodes. Next I will consider that I am including first object in the solution. If I am including in the first object in the solution, then nothing will change. I'll get the same cost and same upper bound. Same cost and same upper bound. Next thing I will consider that first object is not included in the bag. If the first object is not included in the bag, then what will be the cost? First object's profit and weight, second object's profit and weight, third object's profit and weight, and fourth object. See, this I am not including, so I should take only these. So this is how much? 10. Still how much is remaining? 5 kgs are remaining. So 18 by 9 into 5. So this will be 10, 20 and 32. So this will be cost is minus 32. For every node, I should also check one more thing, that whether its cost is greater than upper. No, it's not greater, it is equal. So leave it. Otherwise, if it is greater, kill that node. Now what is upper bound? So without this fraction, if I take, this is 10, 20, 22. So minus 22. Is it less than that? No. If you are getting any lesser small upper bound, then we should update that one. I have explored first node. Now which node I should explore? The one with least cost. So I'll be following least cost branch and bound. So this is minus 38, this is minus 32. I should take this one and continue. Second object included in the bag. So what is the cost? It remains same. See, both the objects are included. So upper bound and the cost remain same only. Next. Second object not included in the bag. So if the second object is not included in the bag, let me calculate cost and upper bound. Cost is 10.2 plus 10.4 plus 12.6. This object is not included. So this is how much? 8. Still how much remaining? 18 by 2, 7 kgs I will take. So this is 2. This is 14, 26 and 36. So the cost is minus 36. But without fractions, if I take, this is 22. Upper bound is minus 22. Is it greater than that? Minus 36, is it greater than that? No. So don't kill the node, right? It remains alive. I have explored second vertex. Now which vertex I should explore next? Minus 38, minus 36, minus 32. So out of this, I should explore this one. If I am following FIFO branch and bound, then I should explore this one. So if you explore that also, the number of nodes will be more, the work will be little extra. Least cost method gives you a faster result. Let us explore this node. So below this, the third object is included. Third object is included, the cost remains same only, right? Nothing is discarded. So then, if the third object is not included, then what will be the cost? Let us find the cost and upper bound for this one. Cost is first object and the second object. Third object, we are not including third object. So this is how much total weight is, how much? 6. Now last object is 9. Can I include that one also? Yes, I can include. It's 9. So completely it is filled now. 9 plus 4 plus 2, it is 15. It is exactly filling in. So what is the cost? Cost is 10, 20, 38. So it is minus 38. And what is the upper bound? 10, 20, 18. So that is minus 38. So there are no fractions here. So we got cost and upper bound same only. Now one thing you observe that we got a smaller upper bound. So update that one. So it becomes minus 38. This is minus 38. Now once we got a smaller upper bound, look at other nodes. So this is alive, this is alive and this is alive. But what is the cost of this one? That is minus 38. It is greater than that one. So kill this node. This is also greater than that one. So kill the node. No need to explore. If you explore also, you will be wasting your time. You will not get the answer. Now which node I should pick up for exploration? I have both the nodes. Let us check this. First object included, second object included, third object included. Can I include fourth also? No, it will exceed the capacity. See, up to here it is 12 plus 9. It will be 21, exceeding the capacity. So I cannot go further, so it will be infeasible. Let us expand this one. Fourth object included in the bag. So if I say fourth object included in the bag, cost will be same thing only, minus 38, and the upper bound also minus 38. And fourth object not included in the bag. So this is fourth object not included in the bag, and the cost will be how much? Without fourth object, right? So if you follow this tree, first included, second included, third not included, fourth not included, means only two objects. that is 10 and 10. So 10 plus 10 is 20, minus 20. So this is greater than that one. So kill the node. See, almost all the nodes are killed. Which is remaining? This is alive. So the last node that we got remaining is the answer node. So what is the answer? First object included, second included, third not included, fourth included. So let us take solution. First object included, second included, third not included, fourth included. So what are their profits? 10 plus 10 plus 0 plus 18. So this is 38. So this is the maximum profit what we got. And their weights are 2 plus 4 plus 0 plus 9. This is 15. So this is the solution. And we have solved this using least cost branch and bound method.